Aloha. Welcome to this month's edition of Live from NOIRLab. My name is Jamika, and I am an outreach assistant at the International Gemini Observatory, which is a program of NSF's NOIRLab. Today, joining me as moderator is my colleague, Leilani Losi. So if you are joining us in the YouTube chat, in the YouTube audience, please feel free to post your questions and comments for today's guest, John Blakeslee, throughout the presentation. Leilani will jump in throughout the talk to share your comments and questions with everyone. So please don't hesitate to keep those comments and questions coming throughout the presentation. Okay, so if you are familiar with Gemini Observatory and NOIRLab, we are absolutely happy that you are with us and that you are familiar with Gemini. But if it is your first time joining us or you haven't joined us in a while, then we're going to do a very quick intro to Gemini. Now, the International Gemini Observatory is actually one of 5 programs that NSF's NOIRLab runs, which is the preeminent U.S. National Center for Ground-Based Nighttime Optical and Infrared Astronomy. Gemini Observatory is composed of twin telescopes, Gemini North, located on Mauna Kea at an altitude of just under 14,000 feet or a little over 4,000 meters, and Gemini South, located on north central Chile's Cerro Pachón. Now, Gemini telescopes observe both in the visible and infrared wavelengths of light. Gemini's 8-meter or 26.5-foot reflectors collect this light with mirrors that are coated with a special layer of protected silver rather than aluminum, which is the more traditional coating for large telescopes. Now, the mirror is made of ultra-low expansion glass and is about 20 centimeters thick. And here you can see the very large vents that are opened at night during observations. This cold nighttime air flowing through the observatory helps to produce stable images. Now, with a telescope in both the northern and southern hemisphere, the Gemini Observatory can observe objects throughout the entire night sky. Okay. For a quick science update, we're going to look at our recent press release, and in the video description after the recording is posted, we will make sure that this link to the press release and to this CosmoView video number 31 that I'm about to show you is available for you to view and download after this show. Also, Leilani will post it in the chat as well too for you, as well as the related press release. So astronomers uncovered the briefest supernova-powered gamma ray burst. Using the Gemini North Telescope in Hawaii, astronomers identified the cause of a surprisingly short burst of gamma rays. The source was a supernova explosion, which usually produces a long gamma ray burst, or GRB. Astronomers now think that this and many other short gamma ray bursts are actually supernova-produced GRBs in disguise. They suspect that these gamma ray bursts look shorter because their gamma ray jets aren't quite strong enough to completely escape the collapsing star. Feel free to explore this video along with the related press release and actually all of our CosmoView videos on our NOIRLab YouTube channel. We have a separate playlist for that. Okay, now on to today's guest. So the title of today's presentation is How Fast is the Universe Expanding and Why Does That Matter? And with us today to explain why it matters that the universe is expanding is John Blakeslee. John Blakeslee is an astronomer at NSF's NOIRLab studying galaxies, galaxy clusters, and the expansion of the universe. He completed his PhD at MIT and has worked as a research scientist with the Hubble Space Telescope's Advanced Camera Project at Johns Hopkins University, a faculty member at Washington State University, a staff astronomer with the Canadian National Research Council in Victoria, British Columbia, and the chief scientist of Gemini Observatory. In addition to doing research, he now serves as the head of science staff for observatory support here at NOIRLab. We'd like to welcome you, John Blakeslee, to the show.
Thank you, Jamika.
I've stopped my share so you can start your presentation when you are ready. And just as a reminder to those of you in our YouTube audience, Leilani is going to be interacting with you throughout the presentation with your comments and questions, and she will just pop in and share those when she has them. All right, John, we are very much looking forward to understanding why the universe is expanding and why it's important that we actually know about this.
Okay.
And John, we have a question for you already, actually, before you dive into the main topic. Liz Fleming would like to know, what has been your most exciting discovery so far and why? Maybe it's this one.
Yeah, can you hear me okay first?
Yeah, we sure can, John.
Okay. My most exciting discovery. Well, I guess maybe one of my earlier ones. So I've not discovered anything Nobel worthy or anything like that, but it's always exciting when you find something you don't expect. So my early work involved studies of globular cluster systems, these very dense groups of stars that tend to occupy the halo regions of galaxies like our own. And one time early on, I was studying a population of globular clusters, and I noticed this long, this long curved object, which turned out to be, on follow-up, a much more distant gravitationally lensed galaxy, much earlier in the universe. That's was being lensed by the galaxy that hosted the globular clusters. So we followed it up, and we were able to derive a nice model of the mass, or improve our understanding of the mass distribution of that galaxy. And it was an investigation we weren't expecting, but we noticed something unusual and followed it up and learned something new. So it's always exciting when that happens.
Definitely.
Okay, so I'll jump into the presentation. So I'm really excited to be here to tell you about how fast is the universe expanding and why does it matter. Give you the latest on this. Oops. Let's see. Okay, so the story starts here, this beautiful blue-green planet, and now the present epoch of the universe. So as we look out into the universe, we of course wonder about our place in it and how big the universe is and how could we ever find that out? And this was one planet and it would drift in the cosmos. How can we find out about the size of the universe and the motions of the galaxies around us? And that's a big question. And it begins with, it requires a series of steps to achieve an answer. The first step is just a small geometric step. And it begins with the fact that we know the distances of the galaxies, of the planets within our solar system, including the distance of the Earth from the sun. The history of how we've found that out is very interesting. I don't have time to go into it right now, but let me just say that we know very well that distance from even radar measurements and spacecraft that have traveled throughout the inner solar system and beyond. And that distance from the Earth to the sun, I think you can see my cursor, from the Earth to the sun is about 93 million miles or 150 million kilometers. Astronomers just call it 1 astronomical unit, 1 AU for short. Now, given our knowledge of that distance from the Earth to the sun, we can use something called stellar geometric parallax to figure out the distances to nearby stars. And that's done by measuring the shift of that nearby star with respect to more distant ones as the Earth travels in its orbit around the sun. So the method is illustrated by this figure right here. So we observe a star, say in January, one part of the year, where its position is with respect to the background stars. We wait, or we can continue to observe it. And then 6 months later, we observe it again and see where it appears with respect to those background stars. And what we find, maybe something like this, the nearby bright star from January to July appears to shift a little bit with respect to the background stars. And the size of this shift tells us the distance by this simple geometric analysis, this triangulation that I showed on the previous slide. And for the aficionados, the equation here is distance is equal to 1 over the parallax, where the parallax is the size of the shift, the angular shift of that star, measured in funny units called arc seconds, which is 3600th of a degree, so a very small size on the sky. And then the distance comes out in an even funnier unit called the parsec, which is about 3.26 light years. So astronomers are used to dealing with sort of crazy numbers. But by measuring the shift of a nearby star with respect to distant things that don't appear to move, we can figure out the distance. And the larger the distance, obviously the smaller the shift, it's harder to measure. So this method of geometric parallax only really works well within our own galaxy. Although now with a satellite called the Gaia mission, we can get out to kind of the edge of the galaxy or very nearby satellite galaxies of our own. But we can't measure distant galaxies using this method. To do that, to take a step further in distance, we need to use something called standard candles, which look a little like this. So a standard candle is a type of star or other luminous object that has a known true luminosity, true brightness. And by measuring how bright that standard candle, that star, appears to us, we can figure out exactly how far away it is. So so here's this candle, you move it further away, it gets a little bit dimmer, a little bit dimmer, a little bit dimmer to the edge of our detection ability. And so the distance is inversely proportional to the brightness, it turns out. A standard ruler is very similar, but instead of being the brightness, it has a fixed size. And as you move it further away, by measuring how large it appears to us on the sky, we can figure out exactly how far away it is. So that could be like a specific kind of disk galaxy that's maybe rotating with a specific speed that tells us how large it is. And that by observing how large it appears, we can figure out how far away it is. Now, a very important type of standard candles are known as Cepheid variables, Cepheid variable stars. So these types of stars, we can measure the time it takes for them to vary in luminosity and the true luminosity, the true luminosity is given by the time it takes to vary. So brighter ones take longer to vary, fainter, intrinsically dimmer ones take a shorter time to vary. So if we measure the period of that variation, we know its true luminosity. Then by observing it on the sky, we can figure out how far away it is. And these Cepheid variables that exist in our own galaxy can then be used, this type of standard candle, Cepheid variables, can be used as a bridge to another type of standard candle called type 1a supernovae, a specific kind of exploding star. And these type 1a supernovae are very useful as standard candles for much larger distances because they're very bright and they can be seen across the universe. Okay, so geometric parallax, this triangulation method using geometry, can tell us the distances of stars within our own galaxy and stars within clusters like this beautiful picture of the Pleiades. These stars have Cepheid variables in them, or stars or clusters like the Pleiades do. And then we know the true luminosity of those Cepheids from this geometric measurement. We use those to step further out to other nearby galaxies, like this one, to get the distance to those nearby galaxies. And this use of Cepheid variables as standard candles is what really revealed the true scale, the true size of the universe initially to us. So a bit over 100 years ago, astronomers thought that the Milky Way galaxy was basically the whole universe, and these things that look like little spiral nebulae, glowing clouds, were gas spirals within our own galaxy. But then astronomers, in particular, Henrietta Leavitt and others, identified Cepheid variables in these nearby galaxies, measured their apparent brightness, and were able to find out that these spiral nebulae and other galaxies like this lay beyond the Milky Way, beyond our own galaxy. And this gave rise to the concept of island universes, that each galaxy is kind of a universe unto itself. The universe is much bigger than the Milky Way galaxy on its own. But of course, no galaxy is really an island. They do all kinds of things. They collide, they interact, they come in clusters. This one looks kind of like if galaxies are islands, this is sort of like an archipelago of island universes. This luminous cluster of galaxies, very massive. And going out further into space, if we map the positions of galaxies on the sky, as in this map of 2 slices of the sky using the Sloan Digital Sky Survey, and we plot those positions in terms of distance from us, we're here at the center looking out in these kind of pie slices on the sky, big swaths of sky. We find that galaxies are distributed not really like islands, and not randomly, but kind of in this frothy structure, this kind of foam-like structure out throughout the universe. Each little dot of light is a galaxy. One important thing to point out here, though, actually, is that this figure doesn't really. Let me just point out one thing. So these numbers here are hours: 14 hours, 13, 12. Astronomers like to measure position on the sky in terms of time because the sky rotates overhead, and so these are hours of longitude on the sky. So this is position on the sky and distance away from us. Except it's not truly distance, it's velocity. And the velocity is measured from the redshift of the light, from 0 out to 0.2 here. And the redshift is just the stretching of light as galaxies move away from us. And at increasing distances in an expanding universe, galaxies move faster. And I'll explain why that is. But by measuring this redshift, we know the velocity. And in an expanding universe, velocity is proportional to distance. So therefore, we have an idea of the distance of these galaxies. So this plot is really like the distance as a function of position on the sky. Measuring velocities in the universe is actually quite easy from the redshift, not super easy. It takes a lot of time and effort and very skilled people with advanced instrumentation. But once you have all that, you can measure velocities for thousands of galaxies based on their redshifts, the shift of their light, this Doppler shifting. What's much harder is measuring the true distance. And as I said before, one way is using supernovae. Here's the supernova 2011 DH in the spiral galaxy, Messier 51, the Whirlpool galaxy. And as I said, these supernovae can be used to measure distances. This particular one is not exactly the kind of supernova, the type of supernova that we need to measure accurate distances, but it's just such a beautiful picture taken by this amateur astronomer, Rodney Pommier. I wanted to show it as an illustration. So the measurement of distances is much more painstaking. We have to find these standard candles, measure their brightness, figure out how bright they should be. That tells us the distance. And we basically have to do it one by one. Much more difficult than measuring the velocities.
All right, John, you have another question in the YouTube chat. It is, in your opinion, has climate change on Earth affected other galaxies? And if so, how?
Yeah, good question. So obviously climate change can affect our ability to study other galaxies because it affects the atmosphere, and atmospheric conditions are critical to our studies of other galaxies. But the Earth is so small compared to even the sun in our own solar system, and infinitesimal compared to the size of the Milky Way or the scale of the universe, that what we do here on Earth doesn't affect our cosmic neighborhood. And in fact, there are other planets in our own solar system that have had excessive greenhouse warming, such as the planet Venus has high amounts of carbon dioxide that causes extreme global warming on the planet Venus. That hasn't affected us, but it shows where we may be headed if we don't change the direction of our energy use. Okay, so this is measuring distances to other galaxies. It's very hard. But once we do that, once we go out and measure distances to a number of galaxies and we get their velocities, we find that the velocity, or the velocity is proportional to distance, or the distance is proportional to the velocity. This plot here is what's called a Hubble diagram, and it shows the results of let's see here. I have some notes, but I'm not sure where I am on my notes. So here's an example from at the 10-year project called the Hubble Key project, carried out in the late 1990s and the early part of this century, using the Hubble Space Telescope to measure distances to a large number of galaxies using 5 different methods. And the goal was to measure what we call the Hubble Constant, this constant of proportionality between distance on the sky and velocity that we measure from the redshift. So as I said, they use 5 different methods. They carefully calibrated all of these methods using the Cepheid standard candles. And they found that a Hubble constant of 72 in these funny units of kilometers per second per megaparsec. So a megaparsec is 1 million parsecs. And that turns out to be about 3 million light years, a little more than 3 million light years. And as you see in this graph, what we call the Hubble diagram, as I said, the galaxies at larger distances in megaparsecs move away from us faster in kilometers per second. However, the uncertainty from this study is still pretty large, plus or minus 7. That's about 10%. And we'd really like to do better than that to understand the expansion of our universe in detail. And in order to improve our measurement of the Hubble constant, the expansion rate, and learn about the physics from that, one thing is useful to note is that all of these all of these galaxies at the largest distances all are measured with basically one particular method. That is the brightnesses of supernovae, type 1a or type 2. And so if you want to get the best possible measurement to the Hubble constant, it makes sense to go farthest away. That gives us the best leverage on its value. And the way to do that is using these very luminous supernova standard candles. And so one team in particular has done a lot of work on that in recent years. That's a team led by Adam Rees, a 2011 Nobel laureate in physics. Not for this exact work, but for some related work using supernovae. And as you see from this graph, this is a plot of kind of their distance ladder going from geometry, this parallax measurements of nearby stars to get the distances to Cepheids and determine their absolute brightness as standard candles for nearby galaxies. And then we go from the nearby galaxies using Cepheids to set or determine the true brightness of these supernovae, type 1a supernovae, specific kind, that are good standard candles. And then going from there, that link between Cepheids and supernova, we can go to the distant universe that gives us a good measurement of the Hubble constant on the largest scales and how fast it's expanding. And when they do that, they find the value of this Hubble constant, this constant of proportionality between distance and velocity of 73.2 plus or minus 1.3 kilometers per second per megaparsec. So that's very high precision. That's better than, that's an uncertainty here of less than 2%. Okay, so an interesting fact is that if you were to convert these funny units, kilometers per second to megaparsec, is something like miles per hour per light year, the answer would be 50 miles per hour per 1,000 light years. So that means if you were in intergalactic space, away from any big galaxies that may mess up your measurement because of their gravity. And if there were another galaxy or another object 1,000 light years away from you, it would be moving away at a speed of 50 miles per hour, kind of like cruising distance. So you can almost catch up to it going 60 miles an hour in your car. Of course, it would take many billions of years to catch up to it. But that's the way, that's what this means. So a galaxy at a given distance is moving at this speed. And as you go further, they move faster and faster. 1,000 light years is actually well within our own galaxy. So you have to go far beyond that to measure the Hubble constant.
That's a really fun example, John. Thanks for that visual. We have 2 questions for you in the YouTube chat. The first one is fun, and then the next one I think is a bit more related to what you were just talking about. And so the first question is, if you could live and be a part of another galaxy, which would it be and why?
I just love the Milky Way. I would never change my home galaxy. So I think that's my answer to that one. All galaxies are beautiful, of course, and we should value the galaxy we're placed in.
Great answer. Here's the next question. When was it discovered that the universe is expanding or that galaxies are moving away from us?
So it was really discovered in the 1920s, so just maybe 90 some years ago. And Edwin Hubble was the first one to publish a paper showing that relation between velocity, the speed that the galaxy is moving away, and his estimate of distance. He wasn't actually the first one to calculate a value from the Hubble constant. That was done by a person named Georges Lemaitre. I'm murdering his name. But so now it's known as the Hubble-Lemaitre law, this expansion, the proportionality between velocity and distance. But it was a long road to finding that out. And I'll talk a little bit more about that. And I have an illustration on the next slide of why that is, why galaxies move, why you get this proportionality between velocity and distance in an expanding universe. So I just want to make sure everyone understands that. So here we are in the Milky Way galaxy at the center. And consider a kind of a random distribution of egg-shaped galaxies nearby us in the universe. And the expansion of the universe, you have to remember, is not an expansion of the galaxies themselves. It's really a stretching of space, that the universe itself is growing, space between galaxies is growing. So if we wait a certain amount of time from this time slot in the universe's history, we wait a certain amount of time when the universe is expanded by just 10%. So we go from here to here, okay? So this is just a 10% increase, a 10% stretching of space. And I've just changed the colors of the galaxies from blue to yellow to distinguish from the previous slide. So I've stretched them all the positions by 10%. The galaxy sizes themselves, the galaxies are held together by gravity, so they don't expand. And now I'm going to do it again. I'm going to wait the same amount of time, however many billions of years it takes for the universe to expand by another 10%. And I've changed the color now to red. So I've got these three epochs in time, and I've just illustrated the galaxies with different colors. And now I'm just going to stack them all together and show the positions. Okay, so what you see is that very nearby the Milky Way, galaxies have appeared to move by very little. They've expanded by 10%, but they're only a small distance away. And so 10% of a small distance is a small amount. Galaxies further away up here have also increased their distance by 10% as space gets stretched by 10%, but they've actually moved further in terms of true distance. So, or 10% from here to here and another 10%, so 20%. And so 20% of a larger distance is, of course, a larger amount. And so the time steps are the same, but they've traveled by a larger amount. So that's larger distance divided by the same amount of time gives you a larger velocity. And that's this Hubble-Lemaitre law, that the velocity is equal to some constant that we call the Hubble constant times the distance, with the distance measured from the Milky Way to those other galaxies. And every galaxy would see the same thing. It's not that we are in a special place. Every galaxy would see the other galaxies around them expanding by 10%. So they would measure the same Hubble law, Hubble-Lemaitre law. So that's why in an expanding universe that expands uniformly like this, the velocity increases linearly or in proportion to the distance with this constant of proportionality. Okay, so now you can ask, okay, so that's the universe expanding. Today we see what happens if you turn time backwards and extrapolate back in time when galaxies would be coming closer and closer together at the same proportionality, right? In the same way. And if you do that, you find that they all come back together at the same time, the same distant epoch in the history of the universe that we call the Big Bang. That's when all the galaxies, all the material would come back together. As shown in this kind of little cartoon illustration of extrapolating backwards in the history of the universe. Of course, it turns out that things are not quite this linear and simple. The history of the universe, the expansion history, is much more complicated. And we know that from observations of type 1a supernovae, these standard candles that are very luminous and can be measured to very large distances. What we find is that very early, so here's the Big Bang. This is a plot of Big Bang and time going forward 10 billion years ago, 5 billion years ago. Today, the Big Bang is about 14 billion years ago. And this is essentially the size of the universe, the expansion of the universe. So the universe grew like this. It started slowing down within the first few billion years because of gravity. Gravity of all the matter in the universe, all the galaxies pulling on each other, caused the expansion to decelerate a bit in the early history of the universe. But as the universe expanded, the distances increased and gravity gets weaker with distance. It's the Newton's 1 over distance squared law, which is preserved in Einstein's gravity. And so as the universe expanded, distances got larger, gravity got weaker as the distances got weaker as the distance squared, as the universe got larger. And something else took over about 7 billion years ago. Some other force, like an anti-gravity, took over, and the universe began somewhat mysteriously accelerating. This was a big surprise about 23 years ago, when this was really confirmed by two independent teams, that the universe has now in an accelerating period of its history, that something is counteracting gravity and causing the expansion to speed up, contrary to our expectations. And this is actually what that team, Adam Rees, Brian Schmidt, and Saul Permuter won, and their collaborators, the Nobel Prize for 10 years ago, this discovery of the accelerating universe. We knew it was expanding for the past 90 some years, but it's only in the past 20 years that we've realized that that expansion is actually speeding up. Okay, so what could be causing that? Why would the universe be speeding up? What is this mysterious anti-gravity? Well, it could be, and it does appear to be consistent with something that Albert Einstein called the cosmological constant. So here's Einstein looking at his equations. He came up with many important equations, E equals mc squared from his special theory of relativity. From the general theory of relativity, which describes how gravity worked, he was able to describe the whole expansion history of the universe. And there's a set of equations that describe that history. This is actually called the second Freemont equation, but it's derived from Einstein's equations of the theory of general relativity. And this is not to terrify everyone, but it's actually a lot simpler than it looks. This equation shows the acceleration of the universe, how fast the expansion is happening or how it's speeding up or slowing down, as a function of two different terms. So this is acceleration. How is the velocity increasing or decreasing? There's one term here that has a negative sign, which means acceleration is negative, it's slowing down. And that term, you notice this big G, that has to do with gravity. And that's exactly what people were expecting early in the history of the universe. Certainly the gravity of all the galaxies were pulling on each other and slowing down that expansion. The details aren't too important. It has to do with the matter and pressure in the universe from the material within it. But there's another term, and that comes in with a plus sign. And this plus sign means acceleration positive. That means speeding up. And in Einstein's formulation of general relativity, the plus term was a constant, this kind of funny looking symbol. It looks like an A without the crossbar. It's actually a capital lambda, Greek letter lambda. And it represents energy that permeates the universe, causing it to accelerate within, according to the general theory of relativity. Now, Einstein thought that the universe was static. So he was doing this in 1915, 10 years before Hubble and others discovered that the universe was actually expanding. So he wanted to keep the universe constant, static, not expanding. And so he perfectly balanced this minus term from gravity pulling together and this plus term from this cosmological constant, this energy that pulls it apart, in a model that was like this. This was kind of Einstein's universe initially. He kept it in balance. He tuned up the values, really the value of that cosmological constant. And a more general term for that cosmological constant that we use today is called dark energy. So that the dark energy, the push from dark energy exactly balanced the pull from gravity and kept the universe stable at a constant size. But you can imagine this is not a very stable equilibrium. That a little bit of extra push will cause this to break. A little bit of extra pull will cause the rocket to fly backwards, to overcome the thrust from the dark energy. And so now we know that it's a much more complex history of the universe, that early on gravity dominated. Now the dark energy is causing it to accelerate as the gravity has weakened. And here's an illustration done by a NASA mission showing the history of the universe going back 13.77 billion years ago to the quantum fluctuations that caused the Big Bang and the rapid period of expansion called inflation, until the universe cooled enough, or soon after the inflationary period, the universe cooled enough that all this hot gas, this plasma that permeated the universe, became neutral, that electrons combined with protons to make neutral atoms. And once that happened, the photons in the universe were able to move freely. They weren't, plasma is basically opaque to photons. They just scatter off of all these ionized particles. But about 375,000 years after the Big Bang, the expansion caused the universe to cool enough that the material became neutral and could begin forming structure. And then there was a period between that when the universe became neutral and kind of transparent to photons, when there was essentially no light. The photons were just streaming without interacting with anything, until gravity caused structure to form, the first stars and galaxies. And we can observe this because telescopes are like time machines. We look back in time. It takes time for light to reach us. We can observe the history of formation of galaxies in our universe to the beautiful spirals that we see today. Now, this illustration was made by NASA to illustrate the way one particular mission that studies the cosmic microwave background works. In that case, it was WMAP. A more recent mission by the European Space Agency is called Planck. And these satellites look back in time to the cosmic microwave background, and they study the light from that time soon after the Big Bang. Before going on, I just, one thing about this plot, okay, so it also shows the history of the expansion. The universe started to slow down a little bit, but more recently it's speeding up. The dark energy is causing this expansion to speed up, the acceleration from dark energy. This plot and many others that are made like it are a little bit misleading, because it makes it look like the Big Bang happened one direction in space. Like you can point over here and it's got to look over here to see the cosmic microwave background and the Big Bang, and the Big Bang happened in one direction in space. And that's not the way it really happened. More accurate representation might be something like this, that the Big Bang happened everywhere in space. The whole universe participated in the Big Bang. And that's represented by placing us kind of at the center. Now, this again is just our perspective. And the light from the cosmic microwave background, which is this hot plasma, or the structure that we see in the hot plasma as it cooled after the Big Bang, comes to us from all directions. And we see the galaxies at closer distances. But by looking in any direction in the sky, we can see light from the Big Bang, because it happened everywhere in the universe in one particular point in time, about 13.8 billion years ago. So in this sense, we're at the center of a glowing sphere of cosmic radiation. And because it takes time for light to travel, every galaxy, every observer on every one of these galaxies would see the same thing. So if you're up here at this little galaxy that looks like it's on the edge of the cosmic microwave background, sort of in the dark ages of the universe, that the observer in that galaxy would see us on the edge, because light would take 14 billion years to get to it. And the Milky Way did not exist 14 billion years ago. We were in that same plasma state. So any of these galaxies would see themselves at the center of this expanding universe, and see the cosmic microwave background in every direction. And so the cosmic microwave background is this really wonderful thing with lots of structure. And as I said before, we have these satellites that are studying in great detail. The first fluctuations in the cosmic microwave background were discovered, I think, around 1992, sometime in the 90s, by one satellite called COBE. There was another one called WMAP about 10, 15 years ago. The most recent one that's still operating, I believe, is the Planck Mission. There's this paper that came out just last year, 2020, presenting the analysis of this Planck satellite observations of the cosmic microwave background through the year 2018. So I don't know, 6 or 7 years of observations, and giving an analysis of the cosmic microwave background. So I'm just showing this to show this really big group of really smart people studying the cosmic microwave background to try to understand what it means. And here is a plot, a map of the cosmic microwave background radiation, showing the structure that we see. And this structure represents deviations in temperature. And those deviations in temperature have to result from deviations in density, fluctuations in density in the early universe. Quantum fluctuations, most likely. Anyway, so by analyzing the structure in this density distribution in the early universe, we can figure out an awful lot about the properties of the universe at early times. And the way they do that in this paper from 2020 and in previous papers that are similar is by something that's called a spherical harmonic analysis. So they look at the structure at many different scales on the sky and the cosmic microwave background, and they try to understand how that structure arose. In detail, it's called a spherical harmonic analysis, but you can think of this as kind of like the harmony of the universe. And so this is a detailed plot showing the structure, and the blue line is the model, how well the line meets the points tells us how well we understand the structure of the universe. Okay.
Okay, John, you have 2 questions in the YouTube chat for you.
Yes.
Our first one is, your graphs and visuals are intriguing. As a novice stargazer, is there a resource that can help me analyze and comprehend them for maximum information?
The visuals, meaning like the images. So for instance, this cosmic microwave background came from the team, the map came from the team who studied it. I think I took it from their paper that's published and is open access. So anyone could find these images.
How about the image of the galaxy in the center and those like waves coming off from it?
Oh,
yes.
That's just me playing around with PowerPoint and drawing circles and squiggly lines, and then putting in a little line of the cosmic microwave background in there. So I'm sure people could do much better. Some people that are very skilled in using graphic software. So this is really a simple representation. And actually, I took it from a guy named John Karlstrom, who's a professor at the University of Chicago, kind of one of my role models in astronomy. And he did it. I saw his talk. He just did it, drawing it on a board. So this isn't much more advanced than that. I'm sure you could do a better job than I did here.
Well, I think our audience would agree that this is a pretty great visual that you made very quickly. So maybe we'll talk to the NOIRLab graphics team about making an even better one that you can use for all your future talks too.
Okay, and John Karlstrom, I'm sort of quoting him here as saying that we're at the center of a glowing sphere, the cosmic microwave background. He specifically studies the cosmic microwave background. I study the galaxies. So was there another question?
Yes, the second question is, has the recent detection of gravitational waves changed the understanding of these measurements of the cosmic background?
They have lent further support to Einstein's general theory of relativity, right? So that was a prediction from 1916, the existence of gravitational waves, that he made 1 year after his publishing the general theory of relativity. It's a prediction that took 100 years essentially to confirm. but it gives us confidence. So not so much the measurements of the cosmic microwave background, but how we interpret them. So we do these kind of exquisitely, very intricate measurements of this exquisitely detailed map of the cosmic microwave background. And then we need to translate that, as I'll talk about, from the early universe to what it implies to the universe today. And that's done, what we should see in the universe around us today. That translation from the measurements of the cosmic microwave background, 380,000 years, just a flicker in time after the Big Bang, that translation from that early epoch to the modern epoch, 14 billion years later, is really done through general relativity and these equations that Einstein derived for the expansion of the universe, with those parameters tuned up, not like he did it, but based on the observations of the cosmic microwave background. It's a little more complicated. It involves particle physics and what we know about neutrinos and the different particles that existed in the early universe. But really, the key part is general relativity for most of the expansion of the universe. And so the detection of gravity waves just is further confirmation that we do understand gravity, that we do understand the physics of the universe, which makes the problem that I'll talk about in a minute even more confounding. So, okay, so this is the group of smart people that analyzed the cosmic microwave background to get this harmony of the universe, this plot of the structure on different scales. Not sure if I read that. So the universe, the conclusion is that the universe rings like a bell. This is like a sound spectrum. The universe rings like a bell, and the sound spectrum imprinted in the structure in the cosmic microwave background tells us really to a high degree of certainty what the universe was made of when it was born, or very soon after it was born, 380,000 years later, what it was made of at that time, and how much energy it had, what the expansion rate was, and therefore how the universe should continue to grow and unfold over time according to general relativity, which has been confirmed in so many ways, including the detection of gravity waves. And so how it should unfold over time, including how fast it should be expanding today and into the future. And its expansion rate today is this Hubble constant. And so by analyzing these data and fitting the model and figuring out what the universe is made of, you come up with this, a big table of numbers from this plot, from this paper a year ago. And the only one I want to really highlight here is the one I'm talking about, the Hubble constant. From this very careful analysis of the harmonic spectrum of the universe in the cosmic microwave background, they can predict to very high precision, based on the physics as we understand it, what the Hubble constant should be today. H-nought is always today. Zero is a look back time of zero. What is it today? The Hubble parameter, the expansion rate, can change over time. We can figure out what it was at the time of the cosmic microwave background. Using general relativity and particle physics, we can figure out what it should be today. And that answer from the cosmic microwave background is 67.3 or 0.4, plus or minus about 0.5. So something very small. So you could say this is the best ever prediction for what the Hubble constant, the expansion rate of the universe, should be today. So here's the big problem that I want to come to. The problem is that the best local measurements of the Hubble constant from supernovae give these wonderful luminous standard candles, give a value of 73 plus or minus 1.3 in these funny units, again, of kilometer per second per megaparsec. However, the most precise prediction from that analysis of the cosmic microwave background light gives a number that's less, 67.4 plus or minus a half. And that difference between those two, about a difference of only 6, is still several times larger than the uncertainty in the uncertainty that we expect. So it's a difference of 6, but we expect, even if you combine them, about 1.5 or so. So it's a highly significant difference. We don't understand why they don't agree within the uncertainties. So one possibility is we're making some measurement mistake, that we don't really know the luminosities of supernovae, that they're not as actually they're brighter than we think they are, and that would give the answer. That could cause the Hubble constant to be lower. We're just blundering in our measurements. But people have been very careful, and this uncertainty, this error bar, should include our uncertainty in that calibration. Or it could be that the universe just isn't acting the way we think it should be based on general relativity and quantum mechanics. The universe is growing differently than expected. So this would mean that there's some kind of error in the translation of our observations in the early universe to what we see today. We've got something wrong in the physics. We're missing something. Another question could be, well, 67 is pretty darn close to 73. How about we just average the two, call it 70, and we're done? Isn't that good enough? And that's quite tempting. However, I wonder what the astronomer Johannes Kepler would do in this case. So who is Johannes Kepler? I believe he was a Danish astronomer, or maybe he's probably German. German astronomer from the 16th, early 17th century. I mean, he worked very hard to try to understand the motions of the planets on the sky and to explain their orbits. And he was using about 30 years of observations from the great Danish astronomer Tycho Brahe, who painstakingly measured the positions of planets like Mars and all the others as they moved across the sky. And after Tycho died, Kepler kind of inherited his observations and tried to come up with some physical explanation, some understanding, mathematical explanation of how the planets move and orbit the sun. He could tell from the observations that the Earth was not the center. They were going around the sun. And he expected that they would be moving in circles. That was his theoretical bias, because the circle, in his view, was the perfect shape, and the heavens should be perfect. So planets should move in perfect circular orbits. And he tried really hard to get that theory to work, and he couldn't. In fact, he almost did. He almost came up with the right geometry just using circles that worked. But for the planet Mars, there was one observation that deviated by 8 minutes of arc. That's only 1/8 of a degree. So a degree is about the width of your little pinky finger. If you hold it at arm's length, the width of your fingernail and your pinky. So the deviation of the position of Mars on the sky was only about 1/8 of your pinky finger. But he trusted the great observer Tycho Brahe that he had made the proper observations, or at least that Tycho knew what his uncertainties were. And so Kepler felt that he couldn't ignore this deviation, this error, this unexplained deviation of 8 arc minutes. And he wrote in his new Astronomy, Astronomia Nova, since 1609, "For if I thought the 8 arc minutes were unimportant, I could make a sufficient correction to his model. But because they could not be disregarded, these 8 arc minutes alone will lead us along a path to reform the whole of astronomy. And they are the matter of the great part of this work. This small difference of just 8 minutes of arc, just like this small difference of 6 kilometers per second per megaparsecs, may be telling us that our theory, our model is wrong, that the planets didn't move in circular orbits, that the universe doesn't follow the physics as we understand it." So it led him to reform the whole of astronomy. And so I'm all for reforming the whole of astronomy, but before we do that, and follow Kepler in that path, I think it's important, and everyone in astronomy thinks it's important to check these measurements first, as I'm sure Tycho did over the course of his career.
John,
Yes. Go ahead.
really quickly, to follow up this exciting explanation before you get to your next slide, I just wanted to let you know that it is the top of the hour. And if you have the time to continue, we are definitely going to stay with you because this is very engaging and interesting. And I'd like to definitely let the people joining us in our YouTube audience as well. We are still here. Please keep those questions and comments coming. All right, John.
Okay. Thanks. So I'm going to the last part of the talk. Sorry to go a bit over, which is how do we check that supernova measurement using a different technique. And the method that my collaborators and I have used is called surface brightness fluctuations. This is a really simple illustration. It's different than supernovae, a different way of measuring the distances to galaxies. And this is just an illustration using 3 types of stellar systems. This one is a globular star cluster, has about 1 million stars. It's relatively nearby, just 2,500 light years within our own galaxy. This is a dwarf galaxy within our local group of galaxies. It's called M32, a satellite of Andromeda. It has about a billion stars, and a much larger galaxy called M49 in the Virgo cluster. It has about 1 trillion stars. And it's the distances, as I said here, about 2,500 light years, 2.5 million, and about 55 million light years. So on the sky, all 3 of these objects look about the same size. If you're just to measure their angular size, they're about the same. They're about the same brightness, actually. But you can tell right away that this one is much closer because you can start to see individual stars. This one, you can just barely see the individual stars, but you can see that it's not smooth. And this one looks perfectly smooth. So by quantifying the smoothness, you can figure out what the distance is. And that's the method of surface brightness fluctuations. The method's been around for a couple decades. However, recently it's become much more powerful by using the Hubble Space Telescope to get above the atmosphere, to remove the blurring that the atmosphere causes, and allowing us to measure these distances much further away. And moving into the near infrared using Hubble's Wide Field Camera 3, a very powerful infrared instrument. It has optical and infrared that was installed about a decade ago. And so over the past decade, we've been working on this. And I'll just briefly describe what our results are. But again, before going on to that, one more illustration. This is a tight group of galaxies on the sky known as Stephan's quintet. It's actually appears to be 5 galaxies. There's 1, 2 in the middle kind of interacting, 1 down here and 1 over here. These 5 galaxies are not all at the same distance, actually. 4 of them are. 1 of them is about 8 times closer. And by looking at this, you may know right away which one it is. So I'll just cut to the chase. It's this galaxy here is much closer than the others. These galaxies here are 8 times further away. And the way you could tell that by eye is just that you see individual stars. If you were to zoom in this galaxy, it's resolved with the resolution of the Hubble Space Telescope. Whereas these other ones, all the stars blend together. It's a little confusing here because they're big, giant arcs of gas, clumpy gas that's glowing around these galaxies that are interacting. But by just looking at this, with a somewhat educated eye, you can figure out that you're seeing the stars here and it's much closer than the others. This method of surface brightness fluctuations works in a very similar way. We published a paper this year that studied a large sample of galaxies using this technique, the Hubble constant from infrared surface brightness fluctuations, trying to understand this discrepancy between local measurements and the cosmic microwave background. Here's some actual data from Hubble Space Telescope of a negative infrared image of the galaxy IC 3032 at a distance of about 55 million light years in the Virgo cluster. We take this picture, we do very careful modeling of the galaxy light distribution. We subtract that light and zoom in and measure all the little fluctuations in intensity. And the size of those fluctuations tell us the distance. As you move the galaxy further away, those fluctuations become smoother in a very in a very understandable way, in a very predictable way. And so by measuring these fluctuations, we can infer the distance to very high accuracy using Hubble. So we did that for a sample of 60 galaxies, 63 actually. Most of them are big bright galaxies like this because it's easier to measure in that way. An additional 20 were selected for our measurements because they have hosted type 1a supernovae, these standard candles. And so by using surface brightness fluctuations to get distances to galaxies that have had supernovae, we can compare directly our distances to these supernova distances to make sure that we're doing the right measurements. And just to cut to the chase, here are our final results. The 63 galaxies, the distances we measure from surface brightness fluctuations, plotted versus their velocity, how fast they're moving away from us in kilometers per second. And the number we come up with in our Hubble diagram is 73.3 plus or minus 2.5, almost identical to what the supernova result gets from their independent analysis using independent distance measurements. So, and it's not just supernovae and surface brightness fluctuation. There are a few other methods that can be used to measure the local value of the Hubble constant. There are also other ways to measure to predict the local value of the Hubble constant based on the early universe. I won't go into details here. You can read about that in this NOIRLab news story that appeared last week. This is a nice illustration from NOIRLab that was used in that story that appeared last week, showing that the bridge between the early universe and the late universe measurement of the Hubble constant just doesn't line up. The early universe observations predict the Hubble constant should be around 67, and these different methods, including surface brightness fluctuations and supernovae, give a value of around 73. So something's going on and we don't fully understand it. So what could it be? As I mentioned many times now, the cosmic microwave background is telling us what the universe was made 380,000 years after the Big Bang, what it was made of. And at the time, it was dominated, the energy density, the mass was dominated by different stuff than it is today. It was mostly dominated by dark matter, ordinary matter, atoms, light radiation, photons, neutrinos. And because it was so close together, this cosmological constant, or this dark energy, was comparatively weak to all this matter that was bunched together. But by observing those properties and the expansion at that time, we can translate that using physics as we understand it to what the universe is made of today, which is actually mostly dark energy, dark matter, a little bit of atoms, and the neutrinos have mostly gone away, as well as the expansion rate, the Hubble constant. So it could be that we don't fully understand physics, that Einstein's theory of general relativity using the cosmological constant is incomplete, that there's a more complex evolution or more complex change of the size of the universe with time than can be described by gravity and cosmological constant. It could be different types of matter in here. We don't know yet, but theorists are very clever, theoretical cosmologists. They've come up with a lot of ideas. So maybe it's not just gravity and dark energy, maybe dark energy that acts like Einstein's cosmological constant. Maybe it's a different kind of dark energy that behaves differently and causes the universe to expand differently in time, and therefore would give a different Hubble constant today. That disagreement is called the Hubble tension, the disagreement between early predictions and what we observe today. And this group of theorists have come up with an idea called chameleon dark energy, a different type of dark energy that could possibly explain why we don't measure the value that the early universe predicts. But there are a number of different papers, and here's one of my favorites explaining this Hubble tension, the high value of the Hubble constant we observe today as an indicator of a mirror world dark sector. Another possibility. There's this is really my last slide. a very useful paper came out recently by Eleonora Di Valentino in the UK and her collaborators, which gives a nice summary of all the observations of the early universe and the late universe, including surface brightness fluctuations, analysis of the significance of the disagreement, and a review of all the possible solutions. No solution appears perfect yet. There's some promising ideas, and we're just going to have to wait and keep improving our measurements until we have a solution. So I'll stop right there and take any additional questions.
Okay, we have some questions and comments to close out our show. We have a thanks, an amazing presentation. Thank you for expanding my knowledge base, and a very engaging and well explained with the little clap emoji. We do have one question left to close this out, and it is, how will new tools like the James Webb or the new radio interferometry project that spans many scopes contribute to improving our understanding of these distances and their changes?
Yeah, so I had a final slide that I didn't go to about the James Webb. So the James Webb Space Telescope will allow us to get much better calibration, understanding of the true brightnesses of these fluctuations using red giant stars measured at larger distances. That's a bit technical, but the James Webb allows us to observe much further than the Hubble, so we can calibrate our method of surface brightness fluctuations much better, using the types of galaxies that the method works best for. And we can also go further out, not quite as far as the supernovae, but about twice as far as we can go now. And that will improve our own value of the Hubble constant. Right now we have an uncertainty of about 3%, whereas the supernovae have an uncertainty about a little less than 2%. By using James Webb, we can improve it to the same level of precision, or even better than, well, they will improve their precision as well, using surface brightness fluctuations. So we'll have a much more secure measurement of the Hubble constant. And then by comparing that to the cosmic microwave background, we'll really find out whether we have made some mistake in the measurements or whether it's really new physics that we don't understand and these theorists need to figure out. Sorry, and yeah, and so interferometric measurements using radio arrays can improve distance measurements as well.
Thank you so much, everyone in the YouTube audience, in the chat especially. We appreciate all the great comments and questions. Thank you so much. Is there anything left, Leilani? Any other questions or comments before we wrap up with John Blakeslee?
Nope, that's it. Thank you everyone for joining us, and thank you to John for this awesome presentation.
Yes, John, this has been, at least for me, really, really enlightening. As I read your paper and preparing for this, and the few questions that I had, you very expertly explained. And so when we post the recording, we will include your paper and the reference that you made to the NOIRLab Stories blog and to that our NOIRLab article that came out last week. So we look forward to having a follow-up soon if there is something else to update us on, John. And in the meantime, we'd like to say thank you to everyone for joining us today for Live from NOIRLab. Now, just as a reminder, we have changed our schedule to be monthly, once a month. So you can look for the next Live from NOIRLab the first Wednesday of October. Mahalo nui loa, and have a great rest of your evening. Aloha. And I've ended the